Let's take a look at finding the horizontal asymptotes of the following function if it exists. Our function is f of x equals x minus 4 over the square root of x squared plus 3. And as we want to find these horizontal asymptotes, if they exist, we need to rely on the definition of horizontal asymptote. The line y equals L is a horizontal asymptote of the graph of the function f of x if the limit as x approaches negative infinity of f of x equals L, or the limit as x approaches positive infinity of f of x equals L. So if we are wanting to find the horizontal asymptotes of this function, we will be needing to find the limit as x approaches negative infinity and the limit as f of x approaches positive infinity. Now, in finding limits as rational functions approach positive or negative infinity, you may have relied on this property that the limit as x approaches positive or negative infinity of c over x to the r equals 0, where c is any real number and r is any rational number. Well, we don't have a rational function here, but we're going to try and use a similar strategy to find the limit as this function the limit of this function as x approaches infinity. So let's start by considering the limit as x approaches positive infinity of x minus 4 over the square root of x squared plus 3. Now, with a rational function, I would typically want to multiply both the numerator and the denominator by 1 over x to the degree of the denominator. So let's think about what the degree of that denominator is. Well, the entirety of the denominator is a square root function, and if I look inside that square root function, the highest degree term is x squared. So this is going to be basically the degree of the denominator. And the square root of x squared is equal to absolute value of x. If this kind of throws you off for a moment, consider taking the square root of negative 3 squared. I would have to square negative 3 first, which would give me 9, and then the square root of 9 would give me 3. And notice the result of that squaring first and taking the square root returned a positive 3, whereas we started with a negative 3. So it returned the absolute value of that negative 3. So taking our cue from what we typically do with rational functions, we will multiply both our numerator and our denominator by 1 over absolute value of x. Now keep in mind that we are creating an equivalent function provided that x does not equal 0, because that would cause issues for that denominator. X is not going to equal 0 because for this limit we are asking x to head to positive infinity. So what do we end up with? We end up with the limit as x approaches positive infinity of, in the numerator using the distributive property, we will have x over absolute value of x minus, we'll have 4 over absolute value of x, all over 1 over absolute value of x times the square root of x squared plus 3. Let's go ahead and simplify that denominator a little bit. Keeping in mind that the square root of x squared and absolute value of x squared are equal, we can rewrite this as the limit as x approaches positive infinity of x over absolute value of x minus 4 over absolute value of x divided by 1 over square root x squared times the square root of x squared plus 3. Now we're going to go ahead and combine those two factors in the denominator, and we'll get the limit as x approaches positive infinity of x over absolute value of x minus 4 over absolute value of x divided by, multiplying those together, we get the square root of x squared plus 3 over x squared. Continuing to simplify, we get the limit as x approaches positive infinity. We still have x over absolute value of x in our numerator minus 4 over absolute value of x. And in our denominator, we can now write that as x squared plus 3 and over x squared and 3 over x squared. This x squared is basically a common denominator for the numerator x squared and 3. So we're almost to a point where we can go ahead and take our limit. Let's go ahead and see what we can do about simplifying. Now, recall that the absolute value function is equal to x if x is greater than or equal to 0. It's equal to the opposite of x if x is negative. So note that we're allowing x to head to positive infinity, which means that x is going to be greater than or equal to 0. So we can replace the absolute value of x with just x. So let's do that. So we get the limit as x approaches infinity of x over x minus 4 over x divided by square root x squared over x squared is 1 plus 3 over x squared. Now there is one more thing that I can do to simplify this before I take the limit. This x over x, that can simplify to be a 1. Because x is headed towards positive infinity, x will not be equal to 0. So we're allowed to do that. So then, just to clean this up a little bit, the limit as x approaches positive infinity, we have 1 minus 4 over x over the square root of 1 plus 3 over x squared. Now, as x goes to positive infinity, this function we've just created behaves the same as our original function. They have the same behavior, so limit as x goes to positive infinity of 1 is 1 minus limit as x goes to positive infinity of 4 over x. We can use our property we noted at the beginning. So that's 0. So 1 minus 0 in the numerator. And in our denominator, limit as x goes to positive infinity of 1 is 1. Plus, in our denominator, we've got 3 over x squared. So using our property, that heads to 0 as well. So we get 0. So we get 1 over 1, or 1. So what does this mean? So this means that the line y equals 1 is a horizontal asymptote of f of x because the limit as x approaches positive infinity of f of x equals 1. Now let's consider what happens as x approaches negative infinity, the second possible source of a horizontal asymptote. So considering the limit in the other direction, so the limit as x approaches negative infinity starts off much the same way. So we'll have the limit as x approaches negative infinity of our function, and we still want to multiply by this 1 so that we can create an equivalent form as x approaches negative infinity. So we'll have the limit as x approaches negative infinity of x over absolute value of x minus 4 over absolute value of x divided by 1 over absolute value of x times the square root of x squared plus 3. Now, I'm not going to go through that process of bringing the 1 over absolute value of x into the square root again. It's identical to what we did before. So this is going to be the limit as x approaches negative 1 of x over absolute value x minus 4 over absolute value of x divided by square root of x squared over x squared plus 3 over x squared. And now we need to replace absolute value of x because we can't do anything with it in its current form. Now notice that this time we are headed towards negative infinity, which means our x values are negative. And when our x values are negative, we use negative x, or opposite of x, for absolute value of x. So what do we get? We get the limit as x approaches negative infinity of x over negative x minus 4 over negative x divided by the square root of x squared over x squared plus 3 over x squared. Now keeping in mind that x is headed towards negative infinity, so x will not be 0, we can simplify a little bit. Limit as x approaches negative infinity, x over negative x becomes negative 1. I've got minus and this negative x, so I'm going to turn that into plus 4 over x divided by the square root of x squared over x squared can be 1 plus 3 over x squared. And so now we're ready to take the limit. And as x approaches negative infinity, negative 1 does not change, so we keep that negative 1. As x approaches negative infinity, 4 over x, we can use our property from before, and that equals 0. Moving to our denominator. As x approaches negative infinity, inside my square root, the 1 remains a 1. Plus, and then as x approaches negative infinity, my 3 over x squared approaches 0. So this is 1 plus 0. So we have negative 1 over 1, which is negative 1. So what we can say is that y equals negative 1 is a horizontal asymptote of f of x because the limit as x approaches negative infinity of f of x equals -1. And so for this particular function, we have some interesting behavior. We don't have a single horizontal asymptote. We actually have two distinct horizontal asymptotes. And we can see that played out here in the graph of the function. As x approaches positive infinity, we can see that this function is increasing and getting closer and closer to this horizontal line, y equals 1. And as x approaches negative infinity along the x-axis, we can see that our function is increasing and getting closer and closer to this horizontal line, the line y equals -1. I hope this helps.